This is the Mathematics Education Podcast from mathedpodcast.com. Welcome to the Math Ed Podcast. My name is Sam Otten from the University of Missouri, and today I'm joined by Nick Wasserman, who has recently published an article in School Science and Mathematics, Volume 115, entitled Mathematics and Science Teachers' Use of and Confidence in Empirical Reasoning, Implications for STEM Teacher Preparation, and that was co-authored with Dara Rossi. So Nick, thanks so much for being here.
Yeah, thanks Sam. Appreciate you having me.
Nick is currently an assistant professor in the Department of Mathematics, Science, and Technology at Teachers College, Columbia University. Prior to that, he was at Southern Methodist University, but before you were on the faculty at Southern Methodist, you were actually a student at Teachers College. So I want to start there with your graduate school experiences and who you worked with.
So in graduate school, I worked with Professors Bruce Vogeley and Phil Smith at Teachers College at Columbia University. My dissertation was mostly related to teacher education, in particular, thinking about beginning teachers and their transition to the profession, sort of looking at what they reported to be really useful attributes during that transition time, things that they found to be helpful in terms of that transition, and then talking about, when they felt like those were sort of acquired, whether they were things that they learned during their teacher education program or perhaps things that they, had from their own experiences growing up in the classroom or in their homes, or potentially even things that they learn after their teacher education experience in teaching. So my dissertation sort of revolved around questions of that nature, and my interest in teacher education really stemmed from my own experiences with the UTeach program at the University of Texas at Austin, and then my graduate program at Teachers College. So I think some of those experiences have shaped future directions that I've looked at. So with some of the results from my dissertation, it's and my own experiences in those programs, it's led my interest in teacher education to focus a little bit more directly on teacher subject matter knowledge, which I think sort of frames some of the things that we'll talk about today.
Mm-hmm. And in the School Science and Mathematics article, which is in Volume 115, you look at mathematics and science teachers, and you focus specifically on their approach to validating conjectures or writing justifications, and you look at their confidence in those validations or confidence in the way that they justified it. So I was wondering where your motivation came from for focusing in on this particular topic.
Yeah, I see this work as relating to sort of this overall interest in trying to understand teachers' subject matter knowledge and what becomes important. And in this case, it's particular to larger picture disciplinary reasoning, justification, proof kinds of conversations. Lee Shulman talked about subject matter knowledge, and one of the things that was in there are teachers need to have a sense of the discipline at hand, the principles of inquiry, how new ideas get added and how deficient ones get dropped. And so I think that ties into these larger interests. The motivation specifically for this, I think that teachers become the primary vehicle for students learning about each of these STEM disciplines in school, and so teachers become a really important part of that process. And there's lots of potential, I think, with math and science concepts being taught in tandem, being learned in tandem, because there are so many connections between them. But as I've considered this and talked also with my colleague Dara Rossi, one of the tensions that arises is, there's these connections, and so how do you meaningfully integrate them? But there's also, ways that the disciplines in a larger picture are different, and so how do you meaningfully separate them? So some of the differences are epistemological differences, particularly in this realm about, how are new ideas added in these two fields? How do things get thrown out? What are the acceptable forms of justification and of reasoning in each of these? And so both in science and in mathematics, these are different. And so teachers will be responsible for navigating these tensions. And so I was genuinely curious about whether or not math and science teachers had similar or different approaches in terms of their reasoning to the same set of conjectures, and also then in terms of their confidence in their reasoning.
Yeah, and I think it's really beneficial that you included the confidence dimension, because it's not that in mathematics reasoning we don't use empirical types of arguments or empirical types of justifications. We do use those a lot to explore an idea or to try to get some insight into how we might prove it. So we use that, but it's important to then check that confidence to see, because in mathematics we want to also realize that we can't stop with just the empirical justification. We want to push it to some kind of actual deductive type justification.
Yeah, I think that's a big part of it. In the literature and proofs, deductive proofs aren't always the right way to start talking with students. I mean, there are times when, drawing on particular examples or inductive kinds of reasoning can be a really useful pedagogical tool for helping students understand. But the confidence indicator was sort of a sense of, are teachers just going to stop there? Do they find this believable enough that it's sufficient in the field, or should there potentially be more? And the hope is that at least there are moments where they see the necessity for more justification.
Mm-hmm. Yeah, and I think, too, there was a Stylianides article where he was kind of challenging that idea that a lot of students believe and they put too much confidence in empirical type arguments or just confirming examples. But Stylianides, in his study, he basically, had students trying to justify things, and then after that he asked them, do you actually believe your response is correct? Do you have total confidence in your justification? And then he found that, some students would give an empirical justification, which is kind of mathematically doesn't bring with it perfect certainty, but the students would actually say, well, that was my answer, but I do not totally believe it, or I am not totally convinced by it. It's just that was the best I could do to put down on this paper. And so that, to me, puts into a new light a lot of the past results where, a large percentage of students were found to give empirical justifications. It's maybe they gave those empirical justifications because they weren't able to produce a deductive one, but maybe they put it down on the paper and they still knew that it was flawed, or they still knew that it didn't actually prove it to 100% certainty.
Yeah, I think that's where, that confidence sort of comes into play.
Yeah, you working with teachers, it's good to ask that so that you can actually see not only what justification did they produce, but are they aware that mathematically an empirical type justification isn't enough, and being able to compare that with science teachers, I think is a really interesting kind of setup for the study. So getting into the study more, I was wondering if you could tell us about who the participating teachers were that you had involved, and then what were the tasks that you had them responding to?
The participants were, practicing middle and secondary math and science teachers, and this was with a colleague, Dara Rossi, and so they were primarily from graduate programs in math education and science education that we were a part of. And so that's primarily who the teachers were. Then the teachers engaged in 3 tasks that they were all mathematical in nature. One had to do with the product of 2 odd numbers always being odd, an expression always producing whole numbers, and then a prime number generator, a function that would generate all primes. So they were intentionally selected as 3 tasks where plugging in cases would kind of be a natural approach to sort of starting to reason with these as a way of justifying the truth or validity of some statement. 2 of the claims were true and 1 was false. The one that was false held for many cases before it became false. And these were all universal statements as opposed to existential ones where a particular case would justify. These statements required them to be universally true.
And then in the article, you cite Balicheff's framework and Hurrell and Sauter's frameworks. So I was wondering how you drew from those to devise your coding scheme and how you analyzed the data.
Yeah, I found both of those frameworks and the descriptions within them as potentially useful as I was thinking about these tasks and the participants and the data, and thought that there'd be useful ways of sort of integrating and drawing on both in the data analysis. And so I synthesized them in some ways to flesh out the framework that we used in terms of coding data. There's some more specific details in the article itself.
My guest is Nick Wasserman from Teachers College, Columbia University, and we're talking about his recent article in School Science and Mathematics. Now I'm just curious, we can get right to it. What did you find with regard to the mathematics and the science teachers' justifications, and then what was their confidence that they expressed in those justifications?
Yeah, so, in theory, if the reasoning or justifications that you give would be lower on the taxonomy in terms of these proof schemes, then you should have lower confidence in those reasoning schemes, that all I'm able to provide as my evidence for a certain statement being true or false is some lower on the taxonomy scale, then I would imagine that your confidence in your reasoning would also be lower, and similarly for the higher ends. In a nutshell, we found overall that the mathematics teachers showed slightly more sophisticated responses in terms of reasoning as a whole. The science teachers had slightly higher confidence scores across the board, which that contrast was somewhat interesting. But I think more importantly, one of the things that came out was for the math teachers, there was a positive association in the relation between their proof schemes and their confidence scores that showed up. It was not at all what you would sort of characterize as ideal, where they have virtually no confidence in some of the lower forms and complete confidence in the higher ones. But when looking at the science teachers' responses, what we found across all their cases was that they really had a similar level of confidence, fairly high, across all the different classifications of proof schemes. And so there wasn't the same kind of differentiation, in particular between more inductive approaches and more deductive approaches to their reasoning, that they found those both equally convincing in terms of justifying the claims. I think this comes down to some of the differences, the epistemological differences, and these large disciplinary distinctions between math and science in terms of how those two fields themselves add new knowledge to the field, that I think came out to some degree in terms of this idea about confidence in reasoning.
Mm-hmm. And I'm curious if you traced any of these things to the conjectures that were true versus the conjecture that was false, because sometimes the confidence actually ends up being correct because the conjecture was true. So it's kind of like, oh, well, I was justified to have my confidence because it is a true conjecture. It's like, well, you didn't know it was a true conjecture just from a few examples. But then you had this false conjecture in the mix as well. So I was wondering if the confidence, if you saw some themes playing out in true conjectures versus false conjectures.
Yeah, the one conjecture that was false, which was this prime number generator, I think it's a fairly common example of something that holds for a while in mathematics, but isn't true. If you plug in natural numbers to this function n squared minus n plus 41, then it generates prime numbers for a large number of cases, all the way up until the 41st, that it becomes untrue. And so one of the things we found in that task was, the natural way to approach that for students was plugging in the first, couple cases. Some people, sort of gave their best shot at a test case, not just the first 1, 2, or 3, but they might try plugging in 10 or 15 just to see, if it was holding down the line in the trend. But they didn't have a way often to think about that one. And so I think, the results for that one were a little bit different, because most people, in terms of what they were actually able to generate, were on the lower ends of the spectrum. And then we had sort of some differences in confidence, but we had very few, I think only one, that gave a full sort of rigorous counterexample for why that claim wasn't true. And so everyone's sort of scores were skewed to the left in terms of the proof scheme that they were using. And so I think it was a little bit different because of that.
Mm-hmm. So I'm wondering, too, taking all of these factors that you have brought together in this article, can you boil down for us a large takeaway that you see from this work for the field?
Yeah, for me, the takeaway, it comes down to thinking about teacher education and teacher training. But if integration between the disciplines is really a key idea for STEM education, if that's something that we think should form a big part of what STEM education looks like, that these disciplines are integrated, then for me, when we're looking at preparation and training, that we've got to attend both to disciplinary similarities, ways that they connect, but also to the disciplinary differences, particularly the epistemological ones. Attending to both of those things must be a key principle for preparing STEM teachers if integration is the premise behind STEM education.
we're having discussions here at the University of Missouri about, working with schools on STEM initiatives, and, that's obviously kind of a big push right now. And we're having discussions about whether it should be an integrated model or whether it should be kind of separate disciplines that have some common themes across them. And I think for your article, that's what I found myself kind of thinking about as well. Like, do I place myself on the side of like true integration, or do I place myself on the side of science and math and technology doing harmonious things in tandem rather than like truly integrating?
Yeah, and I think it's a timely question for our fields to figure out. I think the general sense is that we need to improve education in sciences, technology, engineering, and mathematics, and those disciplines all have really nice connections. I think back to my own experiences teaching, and I would use science examples and technology examples, as I was building up some of the concepts, and vice versa, right? In the science classes, they're talking about math content as a part of that. And so, there's these natural ways that they connect, and so there's all kinds of potential. But I think one of the things that needs to still be figured out is how do you maintain the really disciplinary identity of each of those? How do you maintain that? How does each still have the integrity that it needs to for students to be learning about math and science? Because there are some differences in how we approach problems. There are perspectives that we take about making claims and justifying things.
Yeah, and I think to me that's so important for all of STEM, is to really help students experience and get a sense of the way that disciplines justify their claims. Like, what do they back their claims with, and what is accepted as like a good support for a claim. And that STEM is not just a collection of math content and then a collection of science facts and things and then a collection of technology skills. It's actually also understanding the discipline and how claims are supported.
Yeah, and so this was, not something that made it into the article. Part of what we also asked them to do was talk about, are there any really big differences, that you see between science and mathematics, and their responses. These teachers' responses to that, we're sort of all over. Most people said that there really weren't many differences between them, and so I think that only further supports the idea that if we're really thinking about preparing teachers to teach an integrated kind of STEM model, then really getting at some of these bigger disciplinary distinctions and similarities is an important component of preparing them for that work.
We've been speaking about Nick's article in School Science and Mathematics about mathematics and science teachers' use of and confidence in empirical reasoning. And Nick, before I let you go, I have one question left that I ask most of my guests, and this is going to get off topic a little bit, but I think that's okay. If you weren't in mathematics education as your field of work, what would you see yourself doing instead?
Oh, Sam, it's a hard question. I started out as an architect. I wouldn't go back there. Maybe an engineer. I don't know. Maybe we'll go with a brewmaster.
Oh,
a brewmaster at a local craft brewery. We'll say that.
Are you able?
Would be fun.
Do you do a little bit of that as a hobby, or would you just like to do more of it if you had a chance?
Yeah, no, I keep up with it as a hobby, when I can. So mostly to keep up with my own consumption, and it's a good social hobby. So.
Yeah. Well, thanks so much for taking the time out to talk with us about your work.
Yeah, I appreciate the chance to talk with you, Sam. Thanks again.
Thank you. Thank you for listening to this episode of the Math Ed Podcast. If you'd like to support the podcast financially, please use the PayPal donation button at mathedpodcast.com.